Right, welcome back. We are going to continue off from the natural deduction rules that we were doing in the previous video. What you realize is that we have done conjunction, disjunction, and double negation, right? And we have also looked at the definition, and we say that we are aiming for simple and self-evident, right? It should be simple, and you should be able to explain it simply why the case is. Right. So now we want to look at implication. Right. So we said at the beginning of this course, we have got how many operators? We have got the negation, we've got disjunction, we've got conjunction, implication, and if and only if. Also mentioning that this is a derived operator. So the main operations are these four. So we already have done negation. We've done double negation. We haven't really done negation. We've done disjunction and conjunction. Now we look at implication. Right. So if we look at implication, the truth table for implication said if you have got something true, implying something that is always also true, then the implication statement is true. Then if you have got a true antecedent, so this is our antecedent, anti meaning before, and then this is a consequent, right? So if the antecedent is true and the consequent is false, then we are going to have a false implication, right? If the antecedent is false, no matter what the consequent is, the implication is going to be true, right? So what we're going to do is we're going to revisit it like we've been the others. So we want to identify areas when P implies Q is true. We've got three scenarios where P implies Q is true, right? Now, with regards to this P implies Q, we are going to have the following. So we have got, it's true, true, false here. There's nothing unique there. It's true, false, false here. So the only time that P implies Q is true and P is true, right, is of interest to us. Right? So let's look at it in this regard from the other way. If you have got P, if P is true, and then Q is also true, then P implies Q is true. Right? So if you have got this as false, it will be true irregardless. Now, we look at this rule that is sitting in front of us. How do we interpret it in the simplest way possible? Right. So this is our assumption box coming up again. It's an assumption box. It is saying, let us assume phi is true. If we assume that this is true, and then we are able to prove something, right? So you're able to prove something, given that this is true and you're able to prove something, right? If you assume it is true and you're able to prove Q by virtue of being here will be true, then we're saying phi implies that is also true. So that is an implication, introduction. Now one can argue and say, what if it is false? What if it is false? So if it is false, if we end up finding that phi or P is false, the argument still remains true. Right. So there are two scenarios. This is actually true and we are able to prove this, then this is true. If it is false, false implying anything, false implying that will still be true. So this statement will still hold. So we call that implication introduction. And this rule has got far-reaching consequences. Right? For example, right, there is no proof that says 1 + 1 is equals to 2. Right? If you look at the whole concept of calculus, you can go and look and search, but there is no proof that will tell you that 1 plus 1 is equals to 2. But we have come to accept that 1 plus 1 is equals to 2, and we call these axioms. So these are generally accepted or universally accepted truths. Right. So why are they there? Right? They give the basis or the foundation of creation. Right? For example, I can give another example. 1 kg is just a figure of imagination. Right? When people were saying, how do we measure mass? Then they said, this is 1 kg. What were they referring to? Where did they have a kg? So they took something, a stone or whatever it is, a mass, and then said anything that is comparable to this will be called 1 kg. Right? So that is why if you go to the Bureau of Standards and so forth, you find that they've got samples in the event that, say, the whole world will restart, right? They've got a sample of what 1 kg is, what 1 meter is, all the measurements. But there's nothing that can assist us or that we can point to say, where did someone come and say this is 1 kg? Right. So the same applies to the 1 plus 1. 1 plus 1 is equal to 2 is a set of axioms which are the basis of calculus. From these, we then have calculus. In calculus, has allowed us to build cars, we measure speed, we've taken rockets to the moon, we have done everything based on the premise that 1 plus 1 is equal to 2. So even if you can successfully prove that 1 plus 1 is not equal to 2, it doesn't really matter, because with our wrong assumption, the world is still spinning around. We have managed to have all these developments based on the concept of 1 plus 1 being equal to 2. All right. I hope that makes sense. So the premise we are saying, if we are operating under the guise that this is true, then we are able to prove that. So the conclusion itself is self-explanatory. Given that this is true, then this is also true. That is implication introduction. So this is supposed to be implication introduction. Okay. Let's look at implication elimination. So to eliminate an implication, we are looking at the implication itself. It has got 3 areas where it becomes true. Right. In these, we have got one instance where P is true and the others P is false. So if you're given P implies Q is true, it is not enough for you to decide anything about P and Q, right? So what do? You need extra information. If you are given that P implies Q is true and P is true, so P implies Q and P is true, you can conclude that Q is true. That is a unique truth valuation. Right. So this is a unique truth valuation. Right. So over here, remember, only have 2 elements. If we want to look at another one, for example, if you look at this, we are not even going to look at it being false, because we want phi implies that to be true. So that is the only scenario where P implies Q is going to be true and P is true will result in Q also being true. That is implication elimination. So that is straightforward coming from the truth table. So the previous one, implication introduction, I had to explain because these assumptions usually take a little bit of time to understand. But when we're looking at implication, we've got another concept of modus tollens, right? So this scenario happens when you're given that this implies that is true. So this we've already looked at, so we're not going to look at it. It's only true over here. If you're also told now that this is false, which means this is false, this only happens once in the truth table that P implies Q is true and then Q is false. When that happens, you also learn that this is false. If you've been following this series of videos, remember we say that there was a example that we did, and we say that this is similar to not Q implies not P, right? So we see that relationship being used once again here. So if you have got the negation of this, if Q is false, then and phi implies that is false, is true, then not phi has to be true. Right. So if, in other ways, if you've got not Q implies not P, and you also have not Q, then we are saying this is true, and then this is true, therefore not P is also true. All right. So that is modus tollens, and the Latin name for this one is also called modus ponens. Okay. So that is it for the implication side. See you in the next video.